Greetings everyone, I am Muskan from BSc Chemistry Honors First. I am here to explain the chapter of physical chemistry, that is distribution law. Now we will start our chapter. Firstly, we will discuss Nernst distribution law. Nernst distribution study the distribution of solute between the two immiscible solvent in a contact with each other. When a solute soluble in two immiscible solvent is added to a mixture of these solvent, the concentration of both solute in the both solvent layer is different. In other words, we can say the solute distribute itself in the both solvent. For example, when a dilute solution of iodine in water shaken with carbon tetrachloride, the iodine distribute between two miscible solvents. Iodine is about 86 times more soluble in carbon tetrachloride than in water. Due to high solubility, most of the iodine passes into CCl4 layer. In simple words, we can say iodine is distributed between two immiscible solvents, water and tetrachloride. Nernst in 1891 showed when a solute is added to a mixture of two immiscible liquid, in both of which it dissolves, then it distributes itself both the liquid in such a way that the ratio of concentration of the solute in both the liquid remain constant at constant temperature. However, the ratio is constant when only the solute has the same molecular state in both the solvent. That is, the solute neither undergoes association nor dissociation in both of the solvent. The generalization put forward by Nernst is called Nernst distribution law and is stated that a solute distributes itself between two non-miscible solvents in contact with each other in such a way that at equilibrium the ratio of the concentration of solute in both of the layer is constant at a given temperature, provided the molecular state of the solute is same in both of the solvent. If a solute X distributes itself in between both solvent A and B, the distribution law is written as concentration of X in solvent A upon concentration of X in solvent B is equal to C1 upon C2 is equal to K. Here the constant K is termed as partition coefficient or distribution coefficient. Now we will discuss factor affecting the partition coefficient. Firstly, nature of solute. Second one, nature of liquid pair. Third one, temperature. The nature of solute for a particular liquid pair, different solute have been different solubility. Hence, the value of partition coefficient will be different for different solute at a given temperature. It is clearly seen in the table. We will see. Now we will discuss nature of liquid pair. A given solute has different partition coefficient with different liquid pair as shown in the figure. When water and ether are taken as liquid pair and so they are dissolved in a succinic acid, the partition coefficient is 5.423. When water and benzene is taken as a liquid pair and the solute is taken as a succinic acid, its partition coefficient is 0.096. Here we can see that different partition coefficient in different liquid pair. Now we will discuss the third one, that is temperature. The solubility of a solute in a particular solvent change with the temperature. As the temperature is changed, the solubility of a solute in a given liquid pair also change. Therefore, the partition coefficient also change with temperature. The change in the value of partition coefficient for 1 degree rise in temperature is known as temperature coefficient. However, the value of temperature coefficient is generally small. Now we will discuss experimental verification of distribution law. Solution of iodine in carbon tetrachloride of different concentration are shaken with water taken in different bottle. These are allowed to stand undistributed till the two layers are separated out. A known volume of CCl4 and aqueous layer of pipetted out and titrated against standard sodium thiosulfate solution, and the concentration of iodine is determined. The following result from the distribution of I2 and CCl4 and water show the constancy of ratio in the concentration of each layer. Hence, they prove the validity of a distribution law. Now we will discuss condition for the validity distribution law, that is limitation of Nernst distribution law. The Nernst distribution law in its simple form is equal to K1 is equal to C1 upon C2, does not hold under all conditions. Some limitations and condition under which the law is applicable are as follow. First one is temperature are kept constant. The solubility of solute in both the liquid change with the change in temperature. This may result in the concentration in both of the solvent. Moreover, change in temperature may affect the solubility of the two solvents. Therefore, with the change in temperature, a different value of partition coefficient is obtained at every temperature. Hence, the temperature should be kept constant throughout the concentration of partition constant. Second one is the two solvent should be immiscible or separately soluble. The mutual solubility of the two solvents should not be affected by the addition of solute. And the fourth one, the solution should be diluted. Distribution law hold good for dilute solution. As the concentration of solute increase, the deviation from distribution law become more and more pronounced. The molecular state of solute should be same in both of the solvent. This law is not valid under following two conditions: when the solute undergoes dissociation and when solution is undergo dissociation. Now we will discuss modification of distribution law with change in molecular state. Nernst show the ratio C1 by C2 is constant, that is K is equal to C1 upon C2 is applicable only when the solute has the same molecular condition in both the liquid. That means the solute does not undergo association or dissociation in any of the liquid. However, if any of the such changes take place in one or both of the liquid, the distribution law get modified. So let us consider cases in which a solution may associate or dissociate or enter into chemical combination with one of the solvent. Case 1, when solute undergo association in one of the solvents. Suppose a solute X remain in the normal molecular state in phase 1, whereas in phase 2 n molecules of X undergo association to form a complex molecule Xn as shown in this figure. Solute X undergo association in solvent 2. Here two equilibria exist simultaneously. Suppose the total concentration of solute X in phase 1 is equal to C1 and the total concentration of solute X in phase 2 is C2. If alpha is the degree of association of solute in phase 2 is then the concentration of associated molecule in phase 2 is equal to 1 by n C2 alpha. The concentration of normal molecule in phase is equal to 1 minus alpha into C2. Applying the distribution law of the to the distribution of X in the two solvent, we can write concentration of X in phase 1 upon concentration of normal molecule of X in phase 2 is equal to K. Applying the chemical equilibrium to the polymerization process, we can write the equilibrium constant EQ. We can say concentration of associated molecule in phase 2 upon concentration of normal molecule in phase 2 is equal to K equilibrium. By dividing and further solving this equation, we will get C1 upon n under root C2 is equal to constant. This relation is used to determine the value of n, the extent of association of molecule. The value of C1 and C2 are determined experimentally and substituted in equation. Put n is equal to 1, 2, 3 and so on. The value of 4, which nearly constant value of X is obtained, is equal to n. equation has been verified by studying the distribution of benzoic acid between water and benzene. Benzoic acid exists almost entirely as dimer in benzene but in normal state in water. Evidently, the ratio of C1 upon C2 is not constant, hence benzoic does not exist as a single molecule in benzene. A fairly constant value of C upon under root C2 show that the benzoic acid exists as a dimer in benzene. The method to calculate the N has been explained. Case 2. When a solute undergo dissociation in one of the solvent. Let us consider a solute X dissolved in phase 1 in its normal state and undergo dissociation in solvent 2. The two equilibrium exist simultaneously. Total concentration of X in phase 1 is equal to C1 and total concentration of X in phase 2 is C2. The degree of dissociation of the solvent in phase 2 is alpha. The concentration of undissociated molecule in phase 2 is equal to 1 minus alpha into C2. Applying the distribution law in this equation, we can further get our mathematically formula C1 upon C2 into 1 upon alpha is equal to K. On other hand, when the solute is dissociated in phase 1, having the degree of dissociation alpha and remain undissociated in phase 2, the partition coefficient is given by C1 into 1 minus alpha upon C2 is equal to K. Now we will discuss the case 3 when the solute is dissociated in both of the solvent. It is evidence that the concentration of solute in layer 1 is C1 into 1 minus alpha and in layer 2 is C2 is equal into 1 minus alpha, where the alpha is a degree of dissociation of solute. The partition coefficient is given by C2 upon 1 minus alpha upon C1 into 1 minus alpha is equal to K. Now we will discuss case 4 when the solute enter into chemically combination with one of the solvent. Suppose the solute X remain in normal molecular state in the solvent 1, but one molecule of X combined with n molecules of the solvent. The solvent in phase 2 to form X and S molecules. Let the concentration of solute X in normal state in phase 1 is equal to C1 and the concentration of X in normal state in phase 2 is C2. The concentration of a solvent molecule in phase 2 is equal to C. The concentration of a complex molecule in phase 2 is equal to Cc. Applying the distribution law, C1 upon C2 is equal to. Applying the law of chemical equivalent to equilibriums, we get Cc upon C2 into Cs is equal to K1. On dilute solution, the concentration of solvent in phase 2 is in excess. Therefore, its concentration Cs remain partially constant. Now we will see C2 plus Cc is equal to the total concentration of normal molecule and solvated solute molecule in phase 2. Now we will discuss thermodynamic derivation of the distribution law. The derivation of distribution law from the thermodynamic is based on the condition that in the phase equilibrium between the two miscible liquid contain the same solute dissolved in them. The chemical potential of the solute must be same in both of the phases. Suppose a solute is present in two immiscible solvents A and B in contact with each other. The chemical potential in solvent A is mu A and in solvent B is mu B. At equilibrium, the chemical potential of the solute is in the both phases are equal. Mu1 is equal to mu2. From thermodynamic, we know chemical potential of a substance is given as mu is equal to mu naught plus RT ln A, where mu naught is a standard chemical potential of A, is the activity of the solution in the solution. For A component, we will find the value of mu A, and for B component we will find the value of mu B. Hence we will put the both of the values equal to each other. Finally we will get RT ln AA upon AB is equal to mu naught B minus mu naught A. After mathematically we finally get a equation ln AA upon AB is equal to constant. Then we will take exponential and we will discuss AA upon AB is equal to constant. Since the solution are dilute, therefore the activity are equal to the concentration, so equation becomes Ca upon Cb is equal to constant, that is K. This is the Nernst distribution law. It is applicable in the form when the solute is normally distributed in both of the layer. However, it get modified in the case when the solute undergo association, dissociation or enter into chemical combination with one of the solute. Now we will discuss the application of distribution law. There are many application of distribution law in the laboratory and in the industry. Some of these are briefly discussed here. Firstly, we will see in calculating the solubility of the solute in the solvent. When a solute is shaken with the two miscible liquid are in contact with each other at equilibrium, both the solvent are saturated with the solute. Therefore, the concentration at the equilibrium are equal to the solubility of the solute in both solvent. We can write the distribution law as C1 upon C2 is equal to S2 1 upon S2 is equal to K, when concentration and is C1 is equal to S1 and C2 is equal to S2. The solubility of solute is solvent 1 and 2. Hence we know the value of distribution constant, the solubility of the solute in one of the solvent, the solubility of other in the solvent can be calculated. Second one is distribution indicator. Certain solvent can appreciably dissolve even the small amount of solute present in some other solvent. When such a solvent is added to a dilute solution to the solute is some other solvent, most of the solute get distributed into this solvent. Hence it acts as an indicator for the presence of even a small amount of solute. For example, a dilute solution of iodine in water is almost colorless. Iodine is considerably soluble in CS2. Its distribution coefficient between CS2 and water is 400. Therefore, an extremely dilute solution of iodine can be estimated by adding few drops of CS2 to its aqueous solution. A sufficient amount of iodine passes into CS2 and give it a deep violet color. This solution may be titrated against hypo-sodium thiosulfate solution till the violet color of CS2 layer disappear. Hence, CS2 can serve a distribution indicator in a iodometric titration in which iodine is produced during titration. Now we will discuss third application of the distribution law in determining the extent of association and dissociation of the solute in the solvent. Using the distribution law, the molecular state of solvent of the solute in a solvent can be determined in the distribution experiment if the ratio of concentration of solute in both the solvent, that is C1 upon C2, is constant. Then the solute behaves normally in both the solvent. When a solute is undergo association or association in one of the solvent, that is an X molecule are combined to form Xn having a concentration of C2 in it. The distribution law modifies C1 upon under root C2 is equal to K from the value of n, and the molecular mass of the solid in the solvent can be calculated by multiplying the actual molecular mass by m. For example, benzoic acid is a mixture of benzene and water, exists as a dimer in benzene. Hence, the value of n is equal to 2. Therefore, the molecular mass of benzoic acid in benzene is 2 into 122, that is 244. The value of n in above expression can be calculated by one of the following method. First one is by hit and trail method. The value of C1 and C2 are obtained experimentally, and C1 upon n under root C2 is equal to K are put in a following equation. The putting n is equal to 2, 3, 4, the corresponding value of K are calculated. The number which we gives a constant value of K, the correct value of that is the correct value of n. Second method to find the value of n is logarithmic method. We have the equation C1 is C1 upon under root n under root C2 is equal to K. We will also write is in the way C1 upon C2 under over the power 1 by n is equal to K. C1 is equal to C2 having power 1 by n K. Log, we will take log on the both side. Log C1 is equal to 1 by n log C2 plus log K. The two experimental value C1, C2 and C-1 and C-2, we can write log C1 is equal to 1 by n log C2 plus log K, and one or more log C-1 is equal to 1 by n log C-2 plus log K. On subtracting the equation 2 from equation 1, we have log C1 minus log C-1 is equal to 1 by n is common, and log C2 minus log C-2. We will find the value of n by applying mathematically operation, hence n is can be calculated. Similarly, a solute dissociated in the form in one of the solvent in which the concentration is C2, then the distribution law is applicable as C1 upon C2 into 1 minus alpha is equal to K. Thus, the degree of dissociation alpha of a solid is known at one concentration. Then the value of alpha at other concentration can be obtained using the above equation since K is constant. Now we will discuss the fourth application of distribution law, that is in the study of chemical equilibrium involving the formation of complex ion, and it is an important application of distribution law to study the equilibrium involving complex ion. Consider some reaction of Ki and I2. After this, using distribution law, the equilibrium constant of any of two of these reaction can be calculated on the basis of constancy in the value of equilibrium constant. The formula of the complex can be found out. The application of distribution law is determining the formula of complex ion is described as follow. A solution of iodine in CS2 is shaken with water to determine the distribution coefficient of iodine between CS2 and water. A solution of iodine in CS2 of known concentration, say a mole per liter, is shaken with an aqueous solution of Ki of known concentration, say B mole per liter. After the equilibrium is established between the two layers, the concentration of iodine left in CS2 layer is determined volumetric by titrating it against standard sodium thiosulfate solution. The equilibrium constant can be calculated as follows. Let the initial concentration of iodine in CS2 layer is equal to A mole per liter, and the initial concentration of Ki solution is B mole per liter. Distribution coefficient of I2 between CS2 and water is equal to K. The concentration of I2 left in CS2 is C mole per liter. The aqueous layer of I2 reacts with Ki. Therefore, the total concentration of iodine in aqueous solution will be much higher due to the formation of stable complex Ki3. Total concentration of I2, that is free or combined in aqueous layer, is equal to the initial concentration of I2 in CS2 and the concentration of I2 left free in CS2, that is A minus C mole per liter. After this, we will see the reaction Ki plus Ki2 is in equilibrium and form Ki3. Applying the law of chemical equilibrium, we can write K dash is equal to Ki3, concentration of Ki3 upon concentration of Ki into concentration of I2. Taking different initial concentration of I2 and Ki solution, the value of K dash is calculated for each set. The constancy of value of K dash show the formula of complex Ki3 and the complex ion is Ki3 negative. Now we will discuss the fifth application of the distribution law, that is in the process of extraction. Another important application of the distribution law in the process of extraction in the laboratory as well as industry. The laboratory, for instance, it is frequently used for the removal of a dissolved organic substance from aqueous solution with the solvents such as benzene, ether, chloroform, carbon tetrachloride, etc. The advantage is taken of the fact that the partition coefficient of the most of the organic compound is largely in favor of organic solvent. In industry, the process of extraction is used to remove the impurity from the product. The aqueous solution of the substance to be extracted is shaken with an organic solvent in which it is highly soluble. After shaking vigorously, the mixture is allowed to stand for some time. The two layers are then separated using a separating funnel. The organic solvent is reckoned by distillation and used again for the extraction process to be more efficient. Following condition should be fulfilled. First one is the distribution coefficient of the substance between the extracting solvent and the solvent in which it is already dissolved should be very high in the favor of extracting solvent. Sometimes the distribution coefficient in the extracting solvent is artificially increased by making the substance less soluble in the aqueous phase. This can be done by adding some substance which decrease the degree of dissociation to the compound in aqueous phase. For example, acetic acid, which weakly ionize the aqueous solution to be extracted with the ether. A strong acid, say HCl, is added to a solution. Due to ionization of HCl, the H positive ion concentration increased, and due to the common ion effect of ionization, the CH3COOH is suppressed. As a result, there is greater concentration there is a greater concentration of unionized acetic acid, hence the greater amount of acid will be extracted in ether layer. Similarly, the extraction of organic base from its aqueous solution into organic solvent can be increased by adding strong organic base. In general, the solubility of the organic compound in water can be decreased by adding salt, hence its distribution coefficient increase in favor of extracting solvent. This is termed as salting out effect. We can conclude that greater the distribution constant in the favor of organic salt, greater will be the extracted amount. Second one, to recover the maximum amount of substance, the extracting solvent should not be used in one lot, rather it should be in maximum number of installment. This is called multiple extraction or multi-step extraction. The fact that is more efficient to use extracting solvent in small portion rather than in a lot of one lot is illustrated as follow. Suppose a gram of the solvent is present in 1 liter of aqueous solution. We can extract the substance with ether as a distribution coefficient of the substance between ether and water is 2. We can provide with 1 liter of ether which may be used in one lot of 2 installment of 50-50 cc each. Using all ether in one installment, we will get 67% of the total amount will be extracted. When extraction using 500 ml of ether, we will get 75% of the extracted amount. A general formula for the substance left unextracted. A general expression to calculate the amount of substance left unextracted after a given number of operation is derived. That is, Wn is equal to W into Kv upon Kv plus V has power n. Now we will discuss sixth application of distribution law. The distribution law in the determination of degree of hydrolysis. Hydrolysis is defined as the process in which water reacts with salt to form acid and base. Some terms related to salt hydrolysis, that is hydrolysis constant. A general hydrolysis reaction of a salt Ba can be written as Ba plus H2 is equal to Ha plus BOH, has an equilibrium. Applying the law of chemical equilibrium, the chemical equilibrium constant can be written as K is equal to the concentration of Ha and the concentration of BOH upon the concentration of Ba into concentration of H2O. Since the concentration of H2O is very large, it is regulated as partially constant. The expression 1 may be written as concentration Ha into concentration of BOH upon the concentration of Ba is equal to the concentration of H2O. That is a constant KH, where KH is a hydrolysis constant. The expression 2, where HA and the BOH are molar concentration of acid and base product, and HA is a molar concentration of unhydrolyzed salt. The above expression can be written as KH is equal to the free acid into free base upon unhydrolyzed salt. Degree of hydrolysis. The degree of hydrolysis of a salt may be defined as the fraction of the total amount of salt which is hydrolyzed at a point of equilibrium. For example, in an aqueous solution, aniline hydrochloride, 80% of it hydrolyzed into aniline and hydrochloric acid, then the degree of hydrolysis is 0.80%. The degree of hydrolysis is represented as H. The mathematical H is written as H is equal to number of mole of salt hydrolyzed upon total number of moles of acid. Now we will see the expression that the degree of hydrolysis at different type of salt by taking weak acid, strong base, by taking strong acid, strong base. Overall we will get the value of H is equal to under root KH. The application of distribution law is determine the degree of hydrolysis. We can discuss it by taking an example. Aniline and hydrochloric acid is a salt of weak acid aniline and a strong base HCl. Its degree of hydrolysis is determined when both are react with when aniline hydrochloride react with water to form its ion. The value of KH is equal to the concentration of C6H5NH2 and the concentration of HCl upon the concentration of unhydrolyzed salt. After that we will see the determination of concentration of free aniline in the aqueous layer. A known value of benzene layer is taken out, the solvent is evaporated, then the weight of aniline left behind is found. From this, the concentration of aniline in benzene layer is calculated. The concentration of aniline is aqueous layer can be calculated using the distribution law. Second one is we can determine the concentration of free HCl in aqueous layer. From hydrolyzed reaction, it can be cleared that number of mole of HCl set free is equal to the total number of moles of aniline produced. Further, total amount of aniline produced is equal to the amount of aniline present in aqueous layer plus amount of aniline in benzene layer. The concentration of free aniline in aqueous and benzene layer is calculated by in step 1 above. From the value of number of moles of free HCl produced is also calculated from the volume of an aqueous layer and the number of moles of HCl. The concentration of free HCl in aqueous layer can be calculated. Third one is the determination of concentration of unhydrolyzed salt. Again, from the hydrolyzed equation, it has been seen that the number of molecule of aniline hydrochloride hydrolyzed is equal to the total number of moles of free aniline or HCl produced. The quantity of RHS has been calculated in step 3 above. Therefore, the number of moles of aniline hydrochloride hydrolyzed is obtained when this is subtracted to the initial number of moles of the solute of the salt. The number of moles of unhydrolyzed salt can be calculated from the volume of aqueous layer. The concentration of unhydrolyzed salt can be calculated by substituting the value calculated in step 1 to 3 in equation 1. The hydrolysis constant KH can be calculated. The calculation of degree of hydrolysis of aniline hydrochloride. After calculating the hydrolysis constant KH as discussed above, the solution of the salt having concentration C mole per liter. The degree of hydrolysis can be calculated using expression H is equal to under root KH upon C. Thank you. We will discuss its part in further lecture. Thank you. Have a nice day. I hope you will understand